Hi, welcome to a new session of analog circuits. In today's class 2 under PN junction diode, we'll just revise in what we have done in our previous class. That is, we have done with the MATLAB approach of half-wave rectifier. We have selected input as 100 volts and 50 hertz as supply, and diode it is used as a switch, and the output voltage is measured across the resistor. And these are some of the waveforms that we are going to be seeing in today's class, where we have the source voltage, then we have the output voltage. It is also known as the load voltage. So you can see V0 and VL, the lines which are drawn of half wave are shown to be in similar color, indicating that both are same, whether it is output voltage or load voltage. Whereas the current which travels in the circuit, that is treated as IL, known as the load current, you can see the value of the load current, it is reduced to 0.5. Okay, so you know how to obtain the value of current with the help of Ohm's law under input voltage and resistor conditions. Anyhow, our interest in today's class would be what exactly is V input, which is known as Vm sine omega t, and how to calculate the average value of this sine wave, and how to calculate the RMS value of the sine wave. And then depending upon the average value and RMS value, if at all you account the form factor, which is 1.11, how will you obtain these values that we are going to see in today's session. So in our last class, you can see we have seen the forward bias condition and reverse bias condition. Under forward bias, you had a diode which is shown in this direction. Under reverse bias, you can see the negative is connected to the positive of the input supply terminal. And the output waveforms which we have seen in the MATLAB, these are the waveforms. You can see the source voltage is the same, whereas based upon the diode condition, the output voltage for forward bias is in this direction, halfway output, whereas in the reverse bias, this negative peaks are conducting, that is a negative half cycle will conduct, and the current is assumed to flow in anti-clockwise direction in this fashion. Okay, so this is how the waveforms we got in our past class, and the theory value we have learned like this: the input voltage and the output voltage. Okay, so anyhow, after this, let us see what exactly is input voltage. Input voltage is nothing but it's a sine wave whose value is given by V input is equal to Vm sine omega t. And how to obtain the value of average value of a periodic signal? You have V average is equal to 1 by time period, integral value 0 to t, V in dt. But what exactly is V in? V in is Vm sine omega t. So if at all I substitute the value, you can see the cycle, it is keep on repeating for every 2 pi interval. When it has reached from 0 to the highest 90 value, and it reached to 180 value, which is known as pi periodically in radians, and again it has reached to its negative value, which is minus 270, and then it has reached to this value as 360, which is known as 2 pi. So if at all I integrate this value here, the integration is carried out in terms of sine omega t dt. So Vm I'm treating here as a constant value. So Vm by 2 pi is exactly an amplitude value. That's why it's a constant. And integration is applied to the sine omega t under interval 0 to 2 pi. So if at all you take the integration of sine, it will be minus cos, and the upper limit and lower limit, if at all you substitute, you're going to get the value of the average value as 0. Why 0? Because we started at 0. Okay, it reached to the peak value, it ended up into the again 360 value. So for one complete cycle, the average value is 0. Okay, then how to account the average value for at least positive wave or negative wave? That we can also do with the help of same calculation. So here again you can see I have taken the value of V average is equal to, I'm taking the time interval from 0 to pi value, so 1 by pi. Again the lower limit is 0, upper limit is pi, and substituting the value of upper limit and lower limit value, I'm going to get the average value, which is 2 Vm by pi, or it is taken as 0.637 Vm. If at all you plot the output waveform for this is how the output waveform would be. You can see the intervals 0, pi, 2 pi, 3 pi, and the cycle it keeps on repeating like that. For complete cycle, the one cycle, that is from 0 to 360, it is treated as complete cycle. So for that the average value is 0. Whereas if at all you account for the positive peak, or if at all you account for the negative peak. For positive peak, the average time period we got as 0.637 Vm, and similarly for negative peak, if at all you can account, it will be minus 0.637 Vm. Okay, for the same waveform, that is the sine wave, I can calculate the RMS value also. RMS value formula would be nothing but under root of 1 by t. T is the time period, and 0 to t, again time period is taken as 2 pi, and it is nothing but vi square dt. So vi square changes to vm square sine square omega t dt. Now you have to take the constant term outside, that is vm square by 2 pi I have taken outside, and integration is to be applied to be sine square omega t dt. But sine square omega t can be written as 1 minus cos 2 omega t by 2 dt, and I can take this 2 outside, then it becomes Vm square by 4 pi, that is understood, right? And 1 dt, integration of 1 dt would be t, okay, minus cos, integration of cos 2 omega t would be sine omega 2 t by 2, and respectively you are applying the upper limit and lower limit inside the bracket. And if at all you apply the upper limit and lower limit, then you can see Vm square by 4 pi, it will remain as it is, whereas t changes to 2 pi minus 0, minus this is a sine term, and whether it is pi, 2 pi, or any multiple of pi, whether it is a sine term, it goes to 0. So this Vm square by 4 pi multiplied with this 2 pi will give you the answer as Vm by root 2. The pi and pi will get cancelled. In fact, this decimal value will be 0.707 Vm. Fine. Okay. Then the form factor is calculated as the RMS value of the input voltage to the average value of the input voltage. So we just now we have calculated both the values. So this RMS value is 0.707 Vm, and the average value of the input voltage is 0.637 Vm. So this will give you answer of 1.11. Based upon this form factor only, the substations designing is done. In fact, the power plant system or engineering, electrical engineering power systems, when you are dealing with, based upon this form factor only, the stations are maintained like 33 kV, 66 kV. So that is the application of this form factor. Okay. Now, what happens to this output voltage for half wave rectifier if at all you count it only for 0 to pi period, or if at all you take it from 0 to 2 pi period? What exactly is happening? You can see for a complete cycle, for 0 to pi it is on, from pi to 2 pi it is off. So I'm dividing the cycle into two halves like this, and for the negative half cycle the output is 0. So I'm treating this value as 0. The existing waveform is from 0 to pi. The total time period is 2 pi. Okay. Now if at all you substitute these values of upper limit and lower limit, you are going to get the value as 0.318 Vm. So this is a very important factor. See, this value is the average value of the DC voltage. Okay. Now, once this value is obtained, you should be in a position to understand how the average value you can estimate for sine wave, half wave, ranging from 0 to 2 pi, and existing from 0 to pi. So that is what is the difference you should make it out while calculating the average values. Anyhow, if at all you want to calculate the RMS value, that also can be done. So what you should keep in your mind, it is existing, the waveform is existing from 0 to pi only, and the total time period is 2 pi. So that's why 1 by 2 pi, and the value of existing waveform is from 0 to pi, and this is same, that is b input square, that is b m square sine square omega t dt. Again you can take Vm square by 2 pi outside. The sine square omega t dt can be changed into 1 minus cos 2 omega t by 2. Again you can substitute the values of upper limit and lower limit to this part of integration separately, that is 1 dt and minus cos 2 omega t dt. Separate you do the calculation and substitute the value of upper limit and lower limit. You are going to get the value of Vrms of output voltage as Vm by 2, which is known as 0.5 Vm. So this is a very important factor. Now form factor for this particular waveform, it would be 0.5 Vm by 0.318 Vm, and the value is 1.57. So let us go with the MATLAB approach and check whether we are getting the same form factor or not. So for this, I'm going with this MATLAB approach. You can see here 100 volts 50 hertz as input supply given to a diode of 200 ohms. Okay, so in order to obtain the waveforms, I have connected the scopes here. You can see here there is a scope, there is a scope where this source, this diode, this resistor are the same, connected in series only or in series. So in order to know the supply voltage, I have taken a voltmeter connection across the supply, and that connection I have given to this A, showing as from and go to conditions waveform. This waveform you can see A, it is going to this particular point, and from here it is taken to this particular waveform. When you run this, you're going to get the waveform like this, the input voltage and the output voltage. Fine. Okay. And what about the current? See, current for separately I have taken like this. You can see the input, sorry, this is the output voltage, that is load voltage, and the current. You can see these time variations, everything you can look into the MATLAB. So let me show you the values I have taken. See, here I have taken 100 volts and here I have taken 50 hertz as supply. So that's why here it is 100 volts and 50 hertz. Fine. Okay. Diode, it is taken by default. These are the diode parameters. This number resistance, number capacitance of the diode. In MATLAB values they have select. It is by default it is obtained like this value. So keep it as it is, no problem. You can also change this on resistance value. Here it is 0.001, and the power voltage we are keeping over here as 0.8, more than silicon. Okay, so these things you please keep in your mind. I am displaying all these things only you in order to make you understand how we have selected the diode parameters. Fine. And this is a go to block and this is a from block. You can easily obtain, you just keep on searching in the help desk, you are going to get all these values. Okay, and this is the current measurement, this is the voltage measurement. You can see for separately for input I have kept one voltage, and for output I have got another voltage across the resistor. Okay, and here you can see the value 1.567. This is the value what we have obtained for half wave rectifier as a form factor. Okay, so that this is a MATLAB tool, right? So it will be calculating the value exactly based upon the input and output. Fine. So this is what we got as the form factor value for half wave rectifier. This half wave rectifier, in some other tests you can also see the input is shown in transformer form. So here I have taken a linear transformer with the parameters of linear transformer. I'm just displaying over here. You can make a note of this. There you can see a normal power and frequency. They are in volt amperes and hertz rating. Just you take these values in order to solve in a better way. Keep in your mind that when you're selecting this linear transformer, these are the values you have. And if at all you want to change the values, you can change the values and you can check the output. Okay, what is the important catch over here? This linear transformer, the input winding is 230 and this output second winding is 24. That is the important thing. That is not, it's a step down a transformer. The linear transformer is step down to 24 volts. Okay, that you keep in your mind. Okay, and the rest of the values you can keep as it is. We are not going in depth into these values of RMS values, PU per unit values, and inductance values. This all is important for electrical engineering students who are dealing with power systems, power electronics. For basic level, you need not remember all these values. Just keep in your mind that it will be helpful for you to solve this block if at all you select these values in this way. Okay, and what is the supply? Supply you also see here we have 230 volts multiplied with square root of 2. Okay, instead of 100 I have taken this value. This is a value of sine input, single phase input, that is generally we take here as 230 into square root of 2. Okay, now that the rest of the parts are as it is. You have a diode, you have a resistor, and we are taking here source voltage is selected, output voltage is selected, and when I have run through this 0.04 I got the output here as this fashion. You can see here how beautifully the output is. You see the load voltage, okay, is like this, and this is not the load current. Let me change the value. This is not the load current, this is what it is, the output voltage, right? You can change over here for you, making you people to understand. I'm showing this changes over here. Let me change it to V output. So I'll write here as V output, right? VO indicates V output. Okay, the signal is second signal. Now you can see the values in this. So this is the load voltage and this is the output voltage. In fact, what is the load voltage? It's not a load voltage, it's a source voltage. So here also I can change over here like this. In configuration parameters you're supposed to enter. So it is a source voltage, right? So I'll take this one as Vs. That gives you the final answer like this. The source voltage is, see here we have reduced this to 24, right? 24 is important. So here roughly diode values, all these values are taking into the considerations. So the step down voltage it is showing approximately 33. So uh, all these things you should keep in your mind while designing. Okay, and see this supply output voltage. Yeah, so it is 33 and 33. Okay, so some of the drop is also taken into the consideration. That drop is added to the output voltage. That is the thing here. Okay. So this is how you need to remember all the things. And final touch I have given here the all waveforms in a common background like this. We have source voltage, we have output voltage, we have load current, you have load voltage. Mind you, output voltage and load voltage are one and the same. Okay, so let me close this by saving. Okay, yeah, again we are coming back to our analysis what we have done for form factor which we have obtained to be 1.57. So this theoretical calculations in fact, and the practical output calculation we have seen with the help of MATLAB, that is designing. I hope you understand this particular class. Please be in touch with other classes also, because I'm going to complete the entire syllabus of PN junction diode, which is treated as unit 1 for analog circuits, and this is also important for gate preparation, and this is also important for using of a software MATLAB tool in order to simulate this kind of waveforms, and in order to understand the exact concept of analog circuits or any electronic circuits or electrical circuits. So the final outputs are placed so beautifully over here like this. So we have calculated what the form factor for sine wave, it is 1.11, whereas for the DC voltage the value is obtained to be 1.57. So I hope you like this particular class. Please share among your friends, subscribe to this channel, and please press the bell icon for the future notifications. Thank you.